Okay, thank you everyone for coming to the lecture. So this was the example on. Do people remember this from the homework? You remember? That's good. Okay. It's like tricky one. Wait. Okay. If I just tell you that if I write, if I say that the gradient, this is the gradient matrix, and it has what we call a reduced SVD. Do you remember what the answer was?
It's like GG transpose to get like the sigma squared.
Yeah, something like that. But okay, I'll just write it, or one version of the answer. This is the one. There's other ways to write the answer, but this is like a simple way to write that answer. So it's like you can think of this conceptually as, let's see. Taking the SVD of the gradient, and you can think about this as setting all the singular values to 1. And we call this a semi-orthogonal matrix. So it's kind of, because it's rectangular, it's not quite an orthogonal matrix. But I wanted to show you that, so there's someone on Twitter called Jordan0 who calls himself a speed runner. So it's like he wants to train the neural network as fast as he possibly can. And he took like a variant of this method and then add some tricks to it, like momentum. It's like it makes it low precision. And then in order to compute, it's not really obvious how to compute this thing without doing an SVD, and you don't really want to do an SVD when you're training a neural network because it's kind of slow. But so he uses this iteration. So it's a way to compute this term without actually doing SVDs. It's just kind of an iterative method to compute that thing. And it's not. It throws away this learning rate basically. It's a slight variant, but this is the result he's getting. So this blue curve is something called LLM.C, which is like there's like Andrei Karpathy has like a very fast C implementation of training transformer, which is supposed to be like the fastest way to train a transformer, but this guy Kaller can train it in like a fraction of the time using this like special spectral gradient descent method. So the full disclosure is like I'm kind of collaborating with Kaller, so you take everything with a grain of salt, but it's like seems to be actually much faster to use this method. And this all happened in the last like couple of weeks. So actually after we wrote the homework. So just to say like we're trying to teach you some things that potentially matter in practice, which is kind of, but it basically, anyway, the thing that we wanted to say is if anyone wants to like look at this for final project, it's kind of like an interesting problem of thinking about the math of optimization to actually make the optimization go faster. But anyway, that was just to tell you about that. That's not the main point of this lecture. So last time, I think that you were learning about some aspects of representation learning. And there was this idea of developing techniques, contrastive learning techniques that where you try to learn embeddings of your data and you specifically want to like take basically similar data points and map them to like nearby embeddings. And then you want to take a data point from like a very different class and map it to an embedding that's far away. And we call these contrastive learning algorithms. And they're good ways to learn representations. Oftentimes, well, it's a good, sometimes we think of them as somehow unsupervised ways to learn representations. But anyway, that was last lecture. And then I also wanted to remind you that in like one of the even earlier lectures, we were thinking about kind of different perspectives on thinking about what's happening inside a neural network. And there was the idea of kind of neural perspective, thinking about tensors, and then thinking about spectral properties of tensors. So this is just recapping some different things. But in this lecture, not really using that, and using just thinking more abstractly as a neural network as being a map between from a sequence of vector spaces. So every layer of the neural network you can think of it as a vector space. And like one possible goal of doing deep learning is to learn like a really good representation of your data points. And I'm just visualizing that here as the idea of, first of all, the input space, maybe all the different data points of unrelated things are kind of all mixed up together and not really separated or disentangled. And then when we do deep learning, we're kind of hoping that as we move through the network, we kind of get to the representation at the end where like the data points from different classes or like semantically different data points are kind of separated from each other. And like that's then we did a good job. So that's what this is saying, that we want a representation of our data which is perhaps linearly separable at the end of the network. That would be nice. So what I want to talk about in this lecture is the idea that when you pick what your neural network architecture is, it sort of already has an opinion about which data points are similar to each other and which ones are dissimilar, even without doing contrastive learning. So I want to just introduce some tools for thinking about this. And that's all this is saying, is that the neural architecture kind of already expresses some kind of opinion about how similar two data points are, even before you train it. And we'll think about some tools to capture that idea. Okay. By the way, as ever, please just interrupt me if you have questions. Okay. So the idea here is like, I just give you some data and like, I just want you to think about like, just from first principles, ignoring everything you've ever learned in machine learning about how you would actually fit it if you wanted to fit a model to this data. Does anyone have ideas?
Do like a line, and then the line curves down.
So I could somehow just interpolate, maybe. Well, that would kind of do that. Yeah, that's one idea, is just linear interpolation. And that's, yeah. That's, yeah. I feel like, yeah, go ahead. Polynomial interpolation, which is like maybe harder to draw, but maybe I could fit some kind of like quadratic to this. Potentially. It's fun just to, like, you can just, if you just think about this, you can invent a lot of different like function classes and just think about what it would mean to do machine learning with different function classes, and it's kind of like a big jump to get to doing neural networks if you just think about things from scratch, but that's kind of where we are. But so basically there are a lot of classic approaches to doing machine learning where people did just invent their favorite function class and say, hey, we're just going to do machine learning with this function class. So a really classic example is called kernel methods. And it's quite related to what we talked about in the approximation theory lecture, which was maybe lecture 2. But kernel method says we're going to take a kernel, which is basically, you could also think of it as a bump function. And it could just look like a little Gaussian or like a little curvy. And I'm going to place one kernel on the location of each input, if this makes sense. So if I've got 4 inputs, I'll put 4 little bump functions. And intuitively, like, if I've got 4 data points and I have 4 bump functions, then I have enough degrees of freedom to fit the data. So that seems to make sense. And then I'm just going to rescale them with scalar coefficients, just so that they interpolate the data. So it's like 4 bump functions, 4 scalar coefficients, 4 data points. Everything checks out. And I wrote that down here. So I construct my function f of x by summing over, if I've got n data points, I need to sum over n bump functions. And I denote each bump function using this notation k. So the way to understand, okay, and then there's also a scalar alpha, which allows me to reweight the heights of the different bumps. And then, if I have n bumps and n data points, I can definitely fit my data. So it's kind of a natural way just to explain a little bit about what k of x and xi means. Roughly, if looking at this would be like k of x comma 0. And then you should think about this xi as like allowing me to translate this bump along the x-axis to like be centered on that ith data point. Okay, and that's just what this bit says. And then I can define a function space, let's call it big F, to be the set of functions f that can sort of be decomposed in that form. And if I let the number of bump functions actually go to infinity, so I consider like not all possible locations of where I put the bumps, and then I actually allow myself to have infinite bumps, then this is what is known as they call this function space a reproducing kernel Hilbert space. And this was like all the rage, like before deep learning, or like before the recent, or like let's say the last 13 years of deep learning. It was like before that, everyone was doing kernel methods, and they were like considering spaces of functions like this. And instead of choosing your neural architecture, the whole thing was like you pick a good kernel function. You choose a good kernel or a good bump function that somehow captures the structure in your data. And like all the machine learning, sorry, slight exaggeration, but it was like kind of like there were a lot of machine learning papers focused on kernel methods. So that's just a little introduction to kernel methods. And if you just think about it, it's like not so obvious why we don't still use, like why do we use neural networks? Why don't we go back to kernel methods? It's like, you kind of need to think about it, or it may not be obvious. there's a second way, like second kind of classic way of constructing function spaces or doing machine learning, where you actually, this time you think about sort of sampling random functions. So you come up with some way of just sampling random functions. We would call this like some kind of stochastic process. And you just imagine you just keep sampling random functions from your stochastic process, and you sort of throw away. If it doesn't fit the data, you just throw it away. But if it fits the data, you actually keep it. And you're going to somehow end up with this distribution of functions that actually goes through your training data. So that's not actually, if you actually use this method, you wouldn't actually do that procedure of sampling lots of functions. You would actually do something called conditioning the distribution of functions on the training data and getting what we would call the posterior distribution of functions. But intuitively, this is what's going on with this technique. And there's a special way to make this computationally tractable. And it basically amounts to making the way that you generate the functions kind of like a Gaussian thing. And then this thing will become, all the computations that you need to do this procedure become straightforward. Yeah.
If I remember correctly, I think the optimal thing is roughly like a kernel method itself. Is that, how similar are they?
Yeah, that's a really good question. I have a slide, so there's actually, it turns out, as it happens, that there's a close connection between this procedure and the thing on the previous slide with all the bump functions. And that's kind of interesting. Yes. And roughly it's like, we've not discussed yet how to sample these random functions, but we're going to discuss it. But let's just say that we've discussed it already. And the point is that if you sample all of these random functions that are consistent with the data, and then compute the mean of that distribution, you get a single kind of quite smooth function, which is the mean of that distribution over consistent functions. And that turns out to be equivalent to the kernel interpolator of minimum kernel norm for some definition of the RKHS norm. So there's a really close connection. But that should not make sense to everyone because I haven't defined any of those things. Okay. But this is just, okay, here was the slide. So there's three ways now that we're going to think about function spaces. So first of all, this one is the one we just talked about, where you sort of think about, you sample lots of random functions, and then you throw away all the ones that don't fit the data, and you just keep the ones that fit the data. And this will be something called a Gaussian process. Kernel methods are the ones with the bump functions, where we pick our favorite little bump and kind of arrange them to fit the data. And then neural networks are what the class is mainly about. And there's the cool thing, the really interesting thing is that there's all these correspondences. There's sort of a way to get a kernel method from a Gaussian process. There's kind of a way to get a Gaussian process. They're related to each other, and the relation somehow goes both ways. That's all I want to say. But interestingly, there's a way to get a Gaussian process from a neural network. And it holds, well, there's actually maybe a couple ways to do it, but the one that we're going to think about is there's a correspondence where a neural network in a particular limit is equivalent to a Gaussian process. And it's basically when the network is infinitely wide. So you take the width of all the hidden layers and you make them infinitely wide. And then you randomly sample the weights. So you could think about that as like you just keep reinitializing your network and it keeps giving you random functions. If the network is infinitely wide, it turns out that this distribution is equivalent to something called a Gaussian process. So like these connections, if you want to like understand more theoretically about deep learning, it's like interesting to explore these connections because you can sort of relate neural networks to these classical machine learning methods that people really cared a lot about. Then you can ask things like how useful are these correspondences? Do the correspondences actually amount to things which happen in practice? And that's something else you've got to think about. But I'm just going to tell you a little bit about one of the correspondences.
Yeah. These are all like equally expressive, right? Or is there some sense in which one is more expressive than the other?
It's a good question. So the question was, is there a sense in which one is more expressive than the other, or all the different function spaces equally expressive? I think they may just be different in some sense. Like you can look up and you'll find some literature that discusses this. And it's things like the smoothness properties of the functions in the different function spaces may just be different. Like the kernel thing, because it's built out of the bump functions, even though there's an infinite number of them, they may still be kind of reasonably smooth functions. But I think for a Gaussian process, depending on the covariate structure, you can have really like horrendous functions. But interestingly, with that said, like if you take the mean of the posterior of the Gaussian process, it's actually a nice smooth function. So it's like kind of just different. I don't know which one is more expressive, but it's an interesting thing to think about. Okay, let's see. So now I'm going to introduce slightly more formally what a Gaussian process actually is. So this is just a recap of what we just talked about. But basically, if we have some data, we can think about sampling lots of random functions that are the ones that are kind of consistent with the data, and we can get this distribution. And just notice that all the functions are going through the data, but they're kind of random away from the data. And then given that random function, you can ask a couple of questions. Like one is, what does the mean look like? And it's sort of reasonable that the mean might be a lot smoother than all the random squiggly functions. And then you could ask, what is the standard deviation around the mean? And it's sort of reasonable that it should kind of grow as you move away from the data and then shrink to 0 on the data. So that's one way it could look. So the point of a Gaussian process is it gives you a formula, just like a simple thing that you can easily code up. It just involves some matrices and some linear algebra. But it gives you a formula both for the mean function and the standard deviation. In other words, given a set of data, like you've got these like inputs, you can pick a new point on the x-axis. You say, like, I really care about this point on the x-axis. There's a formula that tells you the value of the mean and like what the standard deviation is at that point. And then you can kind of sweep that point along the x-axis, and you can get this mean, and you can get this standard deviation. So it basically gives you a formula for drawing this picture. That's kind of one way to think simply about what a Gaussian process is. And basically the shape of these standard deviations and like quite what this picture looks like depends upon something that we call the covariance structure of the Gaussian process, and that's what we get to pick as like machine learning people using Gaussian processes, is we get to pick the covariance structure. So that's the picture. Informally, I think this is probably the most useful, like, if you just want a quick takeaway, you don't want to go into all the math, this is like quite a useful understanding of what a Gaussian process is just pretend that it's not you don't know what a stochastic process is, like most people honestly don't, but you do know what a random vector is. So let's just think about random vectors. So this is supposed to represent a vector, which I just turned horizontally so it would fit on the page. And imagine that I have a multivariate normal random vector with some covariance matrix and some mean, which is actually 0. Then I could plot like each coordinate of this I get one sample of this random vector, and I just plot it on an axis. So I just plot each entry. So like this one corresponds to this one corresponds to this one. Okay, and I could do that, and then I could just kind of connect the dots. And I could call this somehow building a function from a random vector just by just by connecting the dots. So I could do that if I wanted to. Then I could say, that's kind of, in this picture, it's not that great because neighboring points on the x-axis are like not correlated with each other. And usually if I have like a nice function, I want nearby points to be like similar to each other. So then you say, okay, hey, I'm just going to choose a covariance matrix with a special structure so that the covariance of neighboring entries in the vector is they're very correlated with each other. So I just pick the covariance such that neighboring entries in my vector are very correlated. Obviously, if I permuted all the entries in the vector, it would break that, but I'm not going to do that. So I'm basically going to pick a covariance structure such that neighboring entries are related. And then I would get a picture more like this, where when I connect the dots, the function, it looks like more like a kind of nice function that I like. And then basically a Gaussian process is exactly this construction, but then you let the number of kind of grid cells in your vector, you let the dimension of your vector go to infinity, and you basically pack these sample points more and more closely together, if that makes sense. And then it's like more, does the construction kind of make sense? Just saying, like, if you have a random vector, you can plot its coordinates, and then you can let the number of coordinates go to infinity, and it will just kind of limit to a smooth, like something that's more like a continuous function. Although, does that make sense? I've not really like proved anything here. I've just like given you an intuitive description. Okay, so I think that like if you forget everything else from the lecture, that's basically sort of what a Gaussian process is. So now I want to give you the formal definition. So now we say that we have some input space x, which was like our x-axis in the previous slide. And then for every point in this input space, so kind of for infinitely many points, we let f of x be a random variable. So you kind of think about the function f indexed by its argument x as being like the continuous generalization of a random vector where x is the kind of index about which coordinate you are on the vector. But that's just an informal thought. And then what we say is that because it's difficult to think about infinite dimensional objects, we say that if we choose a finite number of input points and inspect what the random object f looks like on any finite set of inputs, so on any collection of inputs, x1 to xn, where n is finite, we can consider that to be a random vector. Like legitimately, it is a random vector because we're inspecting the function on a finite set of inputs. And if this random vector is Gaussian for any finite collection of inputs, then we would say that f is a Gaussian process. So this is like the formal definition of a the Gaussian process. It's kind of like an infinite dimensional object where if you like take any finite inspection of that object, it's a Gaussian vector, which is somehow related to what we were talking about on the previous slide. Yeah, go ahead.
Given a random vector, how do you verify whether or not it is Gaussian?
It's more like an analytical, like when we use this tool, it's more like you produce something which analytically, like you know it satisfies this definition. It's not, you're very rarely in a situation where you would want to like test empirically if it's Gaussian. So you would have to verify it analytically most cases. And I'm blanking on how exactly you would do that, but there are ways to do that.
So you can define, like in the construction, what the random variables are, like what each function f is, right?
Yes. So if you're going to use Gaussian processes, you will build something which satisfies this definition. And it's not, the thing is, what's difficult about this definition is it's not obvious that anything should satisfy this definition. And like there's a theorem that most people who use Gaussian processes don't know the theorem. But I think there's some kind of, it's called like Kolmogorov extension theorem or something like this. And it's like, there's this area of math which is about like proving that these things exist. But it turns out you actually don't need to know that area of math to actually use this stuff.
And then I was just wondering, like, precisely what is the definition of a Gaussian vector? Like, I can kind of see, like, from the slide how you're just sampling from a Gaussian constructed, but
yes. Like, the simplest Gaussian vector is like a Gaussian vector where the coordinates are IID, and then just for each coordinate, you sample a different Gaussian, and they're not related to each other. That's like a simple one. And then a general one is defined with respect to a covariance matrix. And yeah, I'm probably going to butcher any explanation I give now, but like I would just go on Wikipedia after the class. Another way to think about a general multivariate Gaussian is to like do the IID coordinates and then rotate the space. And like it turns out that's equivalent to, I'm pretty sure that's basically equivalent to a general one with rescaling the coordinates as well. Yeah.
Well, this is just a follow from this, but the dimensionality of the space within which that Gaussian lives would be the number of data points, right?
Well, yeah, but for this definition, in this case, yeah, that would be if I had a finite thing. But this definition is for any collection of n for any n. So it has to hold for all possible collections of inputs. It's just like quite a technical definition. Is it clear or?
Yeah, I guess I was just initially when I first thought Gaussian, I just imagined the Gaussian curve. So I imagined f being Gaussian, but obviously that's not what this is. And then I thought, maybe white space or something, but it looks like, yeah, I understand better now.
Yeah, it's like conditioned on having a set of inputs.
I'm thinking of like a neural network, I guess, applied on some data points. Like that's Gaussian in the sense that, like the functions that it's, I guess, applying on the data points in the dimension at like a space, it's the dimensionality of the data points. Or like, I guess, larger is Gaussian. Like, I guess I'm just trying to reconcile this with like the neural network not being.
Yeah. Okay.
I'm thinking I'm close, but I'm maybe not.
I have a concrete example. So I think I'm just not sure how much further into the lecture it is going to be. But I think it's going to resolve this question. So let me just like plow on, but keep the question. But I just have like a few more high-level things to say, and then I think, oh yeah, I have a picture as well. So okay, let me just go. I think I'm gonna resolve your question. So I should have defined what a standard multivariate Gaussian is, and that's kind of, I'll add that for next time. But so a Gaussian process, this is just to say that a Gaussian process is the thing that generalizes a finite dimensional Gaussian vector to somehow an infinite dimensional random function. And if a Gaussian random vector is described by a covariance matrix, well, actually, this thing that we call a Gaussian process is going to be described by something that we call the covariance function, which tells us at two different inputs what is the covariance between the function at those inputs. So that's how the covariance matrix gets generalized. And an example of a, if in the finite case, the covariance was like e to the I minus j squared, then here in the continuous case, it would be something like e to the x minus x prime squared. So that's how that would kind of generalize. So this is hopefully this slide will help build some more intuition for what we're talking about. Oh yeah, go ahead.
To clarify, by an infinite dimensional function, you just mean a function that accepts an infinite number of inputs?
Exactly. Exactly. So let me just say again that, yeah, exactly, that we have think about, we've got the x-axis, or the real line, as our input space. So there's an infinite number of things on it. And here we're going to consider two examples, x very close to x prime, which is this picture. And basically, we're going to choose the covariance function almost always in our Gaussian process, such that if I sample the random functions and I plot a scatter plot of, so I sample one random function and I get this point for f of x and f of x prime. And then I sample a different random function and I get this point. And I sample a different one. But because we're imagining that x and x prime are close together, the scatter plot that I get is highly correlated. And as x and x prime get closer and closer together, it should sort of concentrate on on the samples being the same. But then as I move the point x prime further away, like now I move x prime over here, so x and x prime are kind of far apart. The function values that I get from sampling the functions are now kind of uncorrelated with each other. If it's a Gaussian process with this kind of covariance structure, which is usually what you have. And basically, it's the choice of what we call the covariance function that actually encodes what we mean by nearby. And for different choices of covariance function, that could mean something else. And just to give you some common examples of covariance functions, one would be to take e to the negative, the squared distance between the two inputs. Another, if we have a multivariate case, it could be to take some kind of dot product between the inputs. It's basically the covariance structure is some kind of measure of similarity between the inputs, and we sort of use that to induce what the correlation structure looks like between different inputs. Yeah, go ahead.
Does this work with language modeling when you're learning an embedding? Because I guess the words are not continuous, right? You can't take a dot product. Then we have an embedding, but that's learning.
Yes, interestingly, the covariance function, yeah, if you have discrete inputs, there are ways to define covariance functions even on weird spaces. The inputs don't have to be the real line. The inputs to the covariance function can be, any input set. So you can extend this construction to kind of weird input spaces. That was one of the reasons people really like kernel methods as well, because they have that same property that, in some sense, a downside of neural nets is usually you know, it's not obvious how to apply it to language. Let's say, okay, we came up with a way to do it. We just, you know, embed all the inputs and then learn the embeddings. But like, it wasn't obvious that that was going to work before people showed that it worked. So people came up with alternatives, and like, this is compatible with, you know, different input spaces, basically.
But I guess like if we were to say that, I don't know, an LLM was a Gaussian process or something, it would mean that whatever like the solutions it finds are both a Gaussian process in terms of its embeddings, and that it's also figuring out the right embeddings for the solution to the Gaussian process. Because the embeddings are, I guess that's
Yeah, so I kind of haven't got to what I precisely mean when I say that we can think of neural networks as Gaussian processes. So I think let's wait to get there and then discuss this a bit more. Okay. So I think, okay, maybe, yeah, this is the last kind of like abstract slide, and then I'm going to start talking about a more concrete example for a neural network. So I hope that that will make things a little clearer. But the last thing that I want to talk about is how, if you're doing machine learning with a Gaussian process, like how you actually make predictions, or like some people would say like how you do inference, like in kind of machine learning speak. But basically, how do you use if you've got training data or you've got inputs, and you want to make a prediction at a point that you haven't seen, how do you actually do that? And roughly the idea is that if you're given inputs x1 to xn, and you know the function values f of x1 up to f of xn, so that's like your input data, is the inputs and the function values. We want to predict f of x star, where x star is like a new test point, a new test input. That's what we want to predict. You just think about stacking these, stacking all of the things, like all of the things you know and the thing that you don't know into one big vector. Because it's a Gaussian process, we know that the joint distribution of this quantity is Gaussian, because that's like the definition of a Gaussian process for any collection of inputs, including like, you know, that includes the n inputs that I was given and the one that I want to predict on. We know that the joint distribution of those things is a multivariate Gaussian just by the definition of the Gaussian process. And then you can say that, hey, if I have a multivariate Gaussian vector and I know its distribution, one of the standard things that tells you how to do is, given the first n coordinates, what is the conditional distribution of the last coordinate? So that's like a standard manipulation that you can do with Gaussian vectors, is just what is the conditional distribution of the last coordinate on all the previous ones. So there's just like a formula for that. It's just called like conditioning with Gaussian vectors or something like that. And that is precisely the formula that gives you this kind of picture. Because basically you take this point x star and you sweep it along this x-axis, and the formula tells you both what the mean of this coordinate is conditioned on these ones, and it also tells you what the standard deviation is. And interestingly, like it's because Gaussians are so well behaved, the conditional distribution of the last coordinate conditioned on all the early ones is itself a Gaussian distribution. So like, yeah, if you take a Gaussian vector and you sort of condition on the first n coordinates, the distribution of the last one is Gaussian. So in particular, there's just a formula for this mean, and there's a formula for this standard deviation, and that's like a closed form expression just involving like evaluating the covariance matrix basically on the input points. So I sort of realize I'm not really telling you explicitly what these formulae are, but they're things that you can just look up. And I honestly think like if you haven't seen this before, it's maybe easier just to have the intuitive explanation, and then you can just like look up what the formulae are if you're interested. Now I want to tell you what this has to do with neural networks, which was kind of the point of introducing this stuff. And there's a result called the neural network Gaussian process correspondence, which is like something that a lot of people have been really excited about over the years. So now forget everything we just talked about and just think about a neural network. And we just think, for the simplest case is arguably like just multi-layer perceptron. So we've got weight matrices, W1, W2, W3, up to WL. And what we can do is we can just, sample the weight matrices randomly, and it gives me the function. The neural network gives me a function. I write that function down, and then I resample the weight matrices, and I get a new random function, and I write that function down. And I just keep sampling the weight matrices over and over again, and it's going to give me a distribution over functions. And I can ask, what is that distribution? What properties does it have? Okay. So let's pretend that we did that. And we generated, in this case, 1,000 random functions by sampling 1,000 set of weights for my neural net. So I reinitialize my neural network 1,000 times. And I want to inspect the functions. So the way I decide to do that is I'm going to pick two inputs, x and x prime. And in general, it could be like x could be a picture of a cat, and x prime could be a picture of a dog. But it's just like two inputs, and I fix them. And then I get my 1,000 functions, f1 up to f1,000. And for those two inputs, I just kind of stack the outputs of the network. So let's just imagine that the output is one-dimensional for simplicity. And I just build a 2 by 1,000 matrix of all the outputs of my random networks. And I'm just going to plot them on a scatter plot and just see what it looks like. Okay, and I actually did this, but I did it like 2 years ago. But I did it on, this is a truck that's in the CFAR10 data set. And this was a 3-layer MLP, and the width of the network, the width of the hidden layer was 1,000. And I did it for 2 pairs of inputs. So input 1 and input 2. So input, first of all, and then second, I did it for input 1 and input 3. And the interesting thing, so what input 2 is actually just input 1. It's the same truck, but with a little bit of jitter in the pixels. Like I just added a little bit of noise to the pixels. And then input 3 it's the same truck, but I just added a lot more noise to the pixels just to show the difference. And then for my 1,000 random networks, this is what the network outputs look like for the first pair, and then this is what they look like for the second pair. So the interesting thing is it kind of looks like the thing that we were talking about, like the Gaussian process thing, where the two inputs which are kind of similar to each other seem to have more correlated random outputs, whereas the two inputs that are kind of a bit less similar to each other, the outputs are slightly less correlated. So now, and then this is displaying it for pairs of inputs. But I could, instead of having 2 inputs, I could make this same table, but I could put 5 inputs and then sample 1,000 networks and then plot that 5-dimensional scatter plot. And then I could ask, does that thing kind of look Gaussian? And my claim is it will, because of this neural network Gaussian process correspondence. For a sufficiently wide neural network, these scatter plots actually are Gaussian. And actually, to really, we would actually have to do what Zach was saying. Is how do we actually know these are Gaussian? That's a good question. I don't know, there's like tests for Gaussianity that if you wanted to run on this scatter plot and you could do that test, but I didn't know how to do that. But my claim is that really they are Gaussian, and it's because the neural network is a wide network that it has to be this case, has to be the case. So what is the formal claim of the correspondence? It's something like this, that if we take a neural network and we sample its weights, we randomly sample the weights, then so long as the network was very, very, very wide, if I pick any finite collection of inputs, basically for any finite collection of inputs, the distribution of outputs is actually a multivariate Gaussian. Which is the definition of a Gaussian process. That was the definition. If you have, for any finite collection of inputs, the distribution of outputs is Gaussian, then that's satisfying the definition of being a Gaussian process. And it also would explain these pictures. And importantly, like what the covariance function is depends on things like what the architecture of the network is and what the nonlinearity is. So there's it's like an interesting result where like, given a particular network architecture, you can sort of expand its width and there will be a corresponding covariance kernel or covariance function that is basically a function of what the network architecture is. And that's what I meant at the beginning when I said that like there's actually the architecture somehow has an opinion built into the choice of architecture about what data points are similar to each other and which data points are dissimilar to each other. And one way to kind of extract that information is to take the architecture to be really, really wide, and you kind of extract this kernel function or this covariance function. So this function of the form like sigma x prime. And maybe sigma depends on things like what the depth of the network is, what the nonlinearity is, and so on.
So I guess in terms of practicality, so because we're making it really, really wide, we're really giving it a good opportunity to overfit. But I guess the idea is because we're taking a random look at overfitting, that sort of, that's fine, it's okay?
Yeah, that's a really interesting question. Let me make some space and just, also like, I think this lecture is on the shorter side, so the more interesting questions you ask, then like the more learning that can be or something. But, okay, basically, so the question is, if the neural network is really, really wide, then intuitively I would think that it's gonna somehow overfit because it has like too much capacity for my data. But the interesting thing about the Gaussian process picture is that, let's say that we have some data and we get this distribution of functions. With one interesting function could be the mean function. So remember that there's not only is there the mean, but these functions are sort of going through the data. And because it's random and because it's Gaussian, you can have there's some probability of getting like a really horrible function, really bizarre. Like one function could actually do something like it goes through this data point and then it goes all the way up here and then it comes all the way back down and then it goes all the way back up. And there's some probability of getting that function. But interestingly, it's very small because like things can't deviate too much from the mean with like very significant probability, basically. And even if they do deviate a lot from the mean, let's say the variance is really high. Oh yeah, well, I can always try to extract what the mean is because I know that the mean is a nice smooth function. So in the context of this correspondence, it's an interesting question to ask, like, how can I get the distribution of functions to actually concentrate on the mean? In other words, what do I need to do to the neural network to get the standard deviation to go to 0 relative to the mean, if that makes sense? Is there something I can do? And I thought about that at one point, and the argument is that, like, if you make the standard deviation that you sample the weights from very, very small, then it actually causes the distribution to sort of collapse onto the mean, and then with very high probability, all the samples are very close to the mean. But I didn't want to dwell. Yeah, it's something to think about. But it's related to. Oh yeah, there's another answer to that question, which is, it's basically like, I'm not sure if Philip talked about that in one of his lectures, but the idea of like neural networks being very, very over-parameterized, but they can still like represent lots of nice simple functions. So like the fact that the network is very, very wide does not imply that you're going to overfit. It just implies that it's possible to overfit. Yeah, go ahead.
Yeah, why did that require you to have like infinite weights for the neural network? And also, for example, if like you sample 100 random network, and then you show it the network by like random Gaussian distribution by sample it, and they you draw the plot, and for the output you still can say it follows the Gaussian distribution. I'm just wondering, it seems like you can do the same thing in your network for like the kernel methods, like you can learn the sufficient statistic, like the mean value and sigma value, without large hyperparameter tuning or without large like training, so you can learn just sufficient statistic.
Okay, so let me try to repeat what I think the questions were. So the first one was, in this construction of this correspondence, why does the network need to be infinitely wide? And then I think the second question, is it like, if there is this correspondence, why do we actually do deep learning the way that we do it? Why didn't we just extract what the kernel is and then just do Gaussian process regression? Or do some kernel method? Yeah, so they're both really good questions. So on the first question, I'm going to talk a little bit about that on the next couple of slides. So it's because the construction relies on a central limit theorem over the width of the network. That's the short answer. So like, for things to converge to this Gaussian distribution, it's because of a central limit theorem, and that requires something being large, and it turns out it's the width. Yeah, the second question, yeah, that's a great question, because some people really thought that we should do kernel methods, but it just seems to be not the case from the way that we see things right now, is that it seems that even if you have an equivalent kernel to your neural net, maybe for several different reasons, you would actually rather just train the neural net and just tune the hyperparameters rather than do the kernel method or do the Gaussian process regression. I think there's probably a few different potential reasons why that's the case. One is, well, first of all, the kernel method, the Gaussian process, ends up having hyperparameters as well, because somehow like the architecture of the network is going to affect what the kernel is. So it's not like it's really a tuning-free thing. And then another thing is like the kernel methods scale much worse with the size of your data set than neural nets do. Like, I think it's like the cost of all the methods is like cubic in the size of the training set, whereas like somehow neural nets kind of scale linearly with the size of your training data. I'm not sure if, I mean, if you train an LLM, you just train it once on the data, and the computational cost is the cost of a forward pass, the backward pass multiplied by the size of your training set. So it's definitely not a cubic dependence on the number of training points. So that's another thing. But I don't know, it's a super interesting question why people use neural nets rather than kernel methods. I think there's maybe not, may still be somewhat open, probably. Yeah, sorry.
I had two questions. So the first is, here we're saying as the width approaches infinity,
Yes.
have people been able to quantify like how close a network gets to a Gaussian process if the width is finite?
That's a great, so the question was, have people, if this is a limiting result that only holds at infinite width, like if you have a finite width network, do we know what the deviations are from the limiting result? I think there are papers on this question. Okay, one answer is like, even in the classic central limit theorem, there's a result called like the Berry-Essen theorem, which tells you about the deviations from like normality of like a large sum of independent random variables and so on. So like you can just like, you could just say, okay, I'm gonna take the Berry-Essen theorem and like turn the handle and like figure it out. I don't quite know if that actually works, but like, it's like Berry, I'm probably not getting the name quite right, but Berry, and then I think it's like Essene.
Okay.
I'm not sure how to pronounce it.
And then the other question I had is earlier in the lecture you said that like people were really excited about this result. And I'm wondering like what the larger effect of the research community has been, like how that's influencing how people think about like developing models.
Yes, that's a great question. I think the short answer is probably it's had probably actually very little impact on what people actually do with deep learning, realistically. It may not be the case, but it kind of seems that way. Maybe at the end, I can talk a bit about some of the potential limitations of the result. But it's like there could have been a version of deep learning where you're like, ooh, okay, I need to solve this deep learning problem. Like, let me write down what my architecture is, take the limit, work out what the kernel is, study the properties of this kernel, and like, okay, now I'm ready to go. Like, but that's just not what, it's more like, okay, just get an architecture that seems reasonable and we'll just try it. And it's like anything that's, I think like there's a lesson which is like anything that's too convoluted of a procedure is actually unlikely to be really capturing what's going on, and you just don't need, I mean, one thing is you just don't need to do that because you can just train the neural net and you just see. But I think there are also limitations of this result that mean it's possibly also potentially not that useful. Yeah, so the point of this lecture is not to tell you like, this is something for your practical toolkit for like going out into the wild. It's more like, if you're interested to really get into the technical details of like deep learning theory and you want to think about the different ways that people have come up with to think about neural networks, like here's one of them. Okay. Yeah.
How many parameters do we need to optimize in Gaussian process?
Well, generally the kernel, the covariance function, could have an arbitrary number of hyperparameters. So it's like, if you're doing just straight up Gaussian process regression, you're gonna pick a kernel function, you get to design it, and you get to choose how many hyperparameters it has.
What's the most typical kernel function we choose, and what is the correspondence to the neural network architecture?
Oh, yeah, I have an example coming up for correspondence to the network architecture. I think like the really simple, so the question was, is there an example of a typical kernel that people use in Gaussian processes? Like the first one that most people introduce is just the squared exponential kernel, which is like e to the negative x minus x prime squared. And then you might introduce a hyperparameter like dividing by 2 sigma squared, where sigma is a hyperparameter, and it controls the length scale of the correlations that the kernel, and like this is a kernel with one hyperparameter. But then you could say, oh, what if x is multi-dimensional input? Then something you could say is like, what if I have 1 sigma per input coordinate? That would be a way to introduce more hyperparameters. Or you could have a different functional form. You could add something to this kernel. That's like the modeling decisions that people in kernel, and you can read up papers and there'll be like a table of like 10 different kernels, and they'll say like, if your problem has this structure, try kernel X. If it has this other structure, try kernel Y. And it's like, it's similar to like, oh, like use a convnet for images and use a transformer for this. And it's just like modeling decisions. Okay, I'm gonna keep going because now I think we may run out of time, I'm not sure. So I didn't actually prove it. I just wrote down a sketch, and I think I'm just going to post a reading about how to actually prove this correspondence. But I'm just going to give you the something high level about how to prove that this correspondence happens. So remember, the correspondence is that an infinitely wide neural network with random weights induces a Gaussian process like the random functions you get are equivalent to a Gaussian process. And the main tool is something called the multivariate central limit theorem, where mainly you just hear about the central limit theorem for a Gaussian random variable with one coordinate. But it turns out there's a generalization of the central limit theorem to Gaussian vectors. And then proving this result is just applying that theorem a couple times and doing the right induction over depth of the network. And I think, honestly, it's been a while since I thought about this, but I think that there's two steps. There's two main steps. One is you pick a single input to the network and you inspect the network at a particular layer. And you show that the activations for that individual input are IID, random variables, which is kind of intuitive that they should be, if you're randomly initializing the network, the different activations of the particular layer on the same input should somehow be IID random variables, but you have to show that. And then once you've shown that, you then consider that a layer, and you consider batching the activations over the multiple inputs, and you sort of think about each activation coordinate, the batch of examples as being a random vector, and then you apply the multivariate essential. Then you think about the next layer as summing over those random vectors somehow, and you do this multivariate central limit theorem. And anyway, I'm not really explaining it, so the short answer is it's there's a central limit theorem. And I'll post a reading if someone wants to go through the details. Yeah, go ahead.
Question. The first question is, you might, as the width goes for infinity, you must be rescaling the weights somewhat, right, when you're sampling?
Yes, exactly.
Is that, and the second question is could you talk a little bit more about why they're going to be independent random variables when you have complex dependencies in the previous layers?
That's okay. So maybe it's not obvious that they are independent, and I think I maybe should not have said that. So I think that's something you've got to show. And I'm not going to go into it, but it's basically because of the network being so wide at every layer that you have a central limit theorem happening at each layer, and that's going to cause the independence. But I'm not giving you a mechanism. I'm just giving you a hand-wavy justification. I'm going to post the reading. But so the other question was, what precisely is the weight initialization, and how does it scale with the width? So I think I have a concrete example of this result in action. So let's just go through it briefly. So I think this is the instantiation of the result for an MLP with a ReLU nonlinearity. And it turns out that all of the calculations, you can solve them exactly for this model. And one of the papers in the reading actually solves this kernel for this architecture. But it's quite an old paper, and it may not be that easy to read. So I wonder if I can post something better on Piazza, perhaps. But basically, we set the nonlinearity to square root 2 times ReLU. And we sample the weights with variance 1 over fan-in. So that's what we would call somehow the standard parameterization in PyTorch is doing 1 over fan-in. It may actually not be the best way to I actually think it's not the best way to initialize the weights in practice, but it's for this statement to hold, that's the initialization you've got to use. So 1 over fan-in variance. And then what you can prove is that the expectation of the network output is 0. This is a network with no nonlinearity on the output. So that makes sense that it's mean 0, because basically the last layer, anyway, because the last layer is a linear layer, the mean should be 0. And then the covariance structure, so the expectation of f of x multiplied with f of x prime takes this, it's called something called the compositional arc cosine kernel. So we take the dot product between the inputs, and then we iteratively apply this function h, we apply h like L minus 1 times, where L minus 1 is the depth. So it's called the compositional arc cosine kernel. It's just a particular mathematical function which happens to correspond to this architecture. Somebody proved it. So this is an example of the result.
Actually, just a clarification. The whole Gaussian process thing, this is for untrained neural networks, right?
Yes,
Okay.
the thing that I told you about, yes. There is another thing that people call the neural tangent kernel, which is supposed to be a Gaussian process characterization of trained networks, but it's like, it also holds under some assumptions, and people have sort of kind of moved away from thinking too much about that at the moment. But there is there's an analogous result which is supposed to hold for trained networks, but I didn't talk about that. Okay. Does anyone have, okay. I think there's like one slide, and then I can take some questions if anyone has more questions. But basically, if you like really buy into this picture, you're like, yes, I believe in the Gaussian process correspondence, and I want to like take this want to see how far I can take this. You might have questions along the lines of, how does the covariance kernel or the covariance structure depend upon my choice of network architecture? How does it depend on like the way I initialize the weights? And could you actually use these considerations to give you like a theoretical way to inform how we pick our architecture, and like how we regularize the weights during training, or like can like this connection actually like inform the way that we do deep learning? So that was like the hope for this type of result, and it seems to have just like not really happened. Like instead we just do transformer, or like there's like a list of architectures, and you just pick one from that list, and we've got some. So it's just like it was a hope of having like a formal analytical way to do like design, like principled design in deep learning, but just like doesn't seem that we actually use it. So I had one thing, I have a blank slide. So there was one thing that I wanted to talk about at the end, which was basically this question of of the weight initialization that we talked about. So the claim was, or that result held if we have a layer with a certain fan in and a certain fan out, and we use this initialization 1 over fan in, which is actually like the PyTorch standard. It's like people call this like Xavier initialization, but it's not obviously actually the best thing to do, although it is the thing that's built into PyTorch. And that's like, I'm just going to give you one quick piece of intuition, which is basically like, if I have, okay, so wait, first of all, why do people believe in this initialization? Why did people come up with it in the first place? And it's basically because it's the initialization that is good at initialization. And that's the same reason that we use it in the neural network Gaussian process correspondence, because the correspondence is about how networks behave at random initialization. And basically, this is the way to initialize if you want to preserve activation magnitudes at initialization. You should initialize this way. Okay, but it ignores like a kind of fact of linear algebra that if you have a matrix where the fan in is much larger than the fan out, so the input dimension, the fan in, is much larger than the fan out, then the special fact about this matrix is it has a huge null space, meaning that a lot of the inputs are going to get mapped to 0. And if you set up things such that at initialization, the activation magnitudes get preserved, well, at initialization, the vectors are hitting the null space, and you're kind of scaling up all the part of the vector which is not hitting the null space. But actually, like once you get further into training, actually the inputs to the layer will kind of align with the non-null space. And then this principle is kind of bad because then things are much too large. Anyway, this is related to something that people call like maximal update parameterization, or MUP, which is like something that if you're like trying to train giant networks, people care about this a lot. Anyway, that's the end. So if anyone has questions, I'll stick around, but thank you for listening.